All right. Anybody have any homework questions? Yeah.
I have just a concept question
Yeah.
about linkages.
Okay.
Why aren't we using relative motion equations on the pin between the two links? Why is the it's like we're pretending like no arm number 2 doesn't exist.
When we calculate the okay, so on linkages. So you have one arm like this, and then a pin connecting it to another arm. And say we're trying to calculate the velocity and acceleration of this point P. Let's call this A and B.
So B, why doesn't B?
So when you're calculating the velocity and acceleration of B, you mean why don't we need relative motion? Okay, well, the question is, so all of these, the points on any of the arms of a linkage is in circular motion around something. So this point P is moving in circular motion around B. That's a terrible circle, but you know what I mean. So the center of the circular motion of P is B, right? And the question is B fixed to the ground or not? Okay. I mean, is that at rest relative to the ground coordinate system or not? In the case of B, that's not. That can be moving. Okay. And so if the center of the circular motion is moving, then you're going to need to use relative motion. Okay. But if you think of the circular motion of B, okay, that's in circular motion around A. So you can calculate the motion of this as circular motion around A. But then is the center of that circular motion fixed to the ground? And in this case, it is.
Okay. So you really are just ignoring arm 2 or whatever effect it's having on B because it's just the center space.
Yeah, I mean, really, you could. So you could think of it. So what if we did do the? What if we did use relative motion for the acceleration of B? Okay, so let's think about that. So the acceleration of B relative to the ground is equal to the acceleration of B relative to A plus the acceleration of A relative to the ground. Okay, and so you can set it up the same way. This is the circular motion of B around A, but the acceleration of A relative to the ground, that's fixed in this case. When you do that relative motion equation for P around B, the second part is something. Any other questions? Yeah.
Excuse me, looking ahead, I saw that there was an exam on the 24th.
Okay, yeah.
So isn't that coming up?
That's a week from Monday.
Right, that's exactly. So we won't have class until Wednesday.
Right.
So we're certainly within a week.
Okay, yeah.
Sure
that's a good point. I'll put some stuff about the test on D2L this weekend.
Okay, cool. Thank you.
Yeah, sure. Any other questions? Yeah. Do you have it with you? Anyone? Okay. Ferris wheel has a radius of 4.5 meters. Rotates with a constant angular speed of 1.2 radians per second. It doesn't say the direction, so I'll choose this way.
Yeah, that was my question.
Okay. Well, yeah, if it doesn't say the direction, either the direction doesn't matter for the answers that you're going to get, or the person who wrote the question is a stupid idiot. They probably won't give him any TAs to help him. And the Ferris wheel is mounted to a car. And the car is accelerating, which is speeding up. Oh, a train car. Well, that's going to have to do. The path of the train car is perpendicular to the plane of the Ferris wheel. Well, I drew that wrong then. Okay, so the path of the train car is, let's say, into the page, perpendicular to the plane of the motion. And this thing is speeding up at 2.5 meters per second squared. Let's say it's into the page. So 2.5 meters per second squared. Sketch the system. Done. And then what's the net force applied to a 50 kilogram person?
Okay, so that X, I would consider that out. That's the
Okay.
arrow tail, and then the arrow head would be the dot inside of it. And if I were sketching it, that would.
Okay.
Do you consider that into the page toward us, or?
That's the back feathers of the arrow, so yeah, I would consider that into the page.
Oh, then I'm wrong. So the acceleration is not.
Right. Correct. That's supposed to be the feathers on the back, and if you draw it like this, that's supposed to be the tip of the point coming towards you.
Yeah, that's what I just said. So
oh.
Why is it?
Okay. There's two things going on. That's why. So yes, you're right that the angular velocity vector of this is out of the page. But then the separate thing going on is it says that it's mounted to this train car that's speeding up. Okay. And so that train car has an acceleration vector. I mean, I could have drawn it. I could have chosen it to be the other way, but that's independent of this. That's just the train. That's the train doing whatever the train does while this thing does whatever it does. And there's a 50 kilogram passenger here. Here. Okay. And we want to calculate the net force. So if you think of this P as the passenger and this C as the center, we can think of the acceleration of the passenger. Let's choose a coordinate system too. So let's go X, Y, and then Z coming out. All right, so acceleration of the passenger relative to the ground is equal to the acceleration of the passenger relative to the train, or that, in other words, the acceleration of the passenger relative to the center, because the center is locked rigidly to the train, plus the acceleration of the center, the train, relative to the ground. Okay. The acceleration of the passenger relative to the center, that's circular motion. So this is going to come from the watermelon equation. And the acceleration of the center relative to the ground, this is the acceleration of the train. So now we can sort of do this in parts. The angular acceleration, it says that it's moving with a constant angular velocity, so this is 0. The r vector, so we're talking about a circular motion from the point C to P, so that's 4.5 meters in the negative y direction. And omega, like you said, omega using the right-hand rule is in the positive z direction with a magnitude of 1.2. So the acceleration of P relative to C is alpha cross r. This is the one that goes away. Plus 0, 0, 1.2 crossed with the quantity 0, 0, 1.2 crossed with that r vector 0, negative 4.5, 0. That's 5.4 in the positive x direction. And then 5.4 times 1.2 is 64.8. 6.48, yeah. So this is and that is in the positive y direction, 6.480. And so now I'll go back to the relative motion equation. The acceleration of the train car is 2.5 meters per second squared in the negative z direction. So the acceleration of the passenger relative to the ground is the acceleration of the passenger relative to the car plus the acceleration of the train car relative to the ground, 0, 0, negative 2.5. Okay. Yes.
One problem while I'm seeing what I'm doing is trying to figure out those offsetting fractions. Like just setting up the equation. You know what I mean? Like
yeah.
U to G, U to C, all that kind of stuff.
Yeah.
Is there a knack or something that can kind of, you know what I mean?
Yeah. Yeah, so practically, like in practice, the way these problems usually work is there's a thing, okay? The thing that you're trying to calculate overall, and there's some kind of like vehicle that's stuck in the middle of everything that the thing's moving relative to, and then there's the ground. Okay, and if you always think of, so usually you can think of, there's an object, there's a vehicle, and there's the ground. And so if you always set it up as the acceleration of the object relative to the ground, is equal to the acceleration of the object relative to the vehicle plus the acceleration of the vehicle relative to the ground. That always works. So I guess that's sort of how I think when I do it usually. That's right. Then it would just be circular motion. Yep. But then, you know, the problem probably wouldn't bother telling you what the vehicle was doing. I mean, I guess if it's trying to make sure that you understand how all this stuff does or doesn't fit together. But, you know, like if we were just trying to calculate the acceleration of the passenger relative to the train car, then we wouldn't have to know what the train car was doing. Okay, so here is a really important question. Oh, I didn't finish this problem. Don't ask that yet. Okay, so now that we calculated the acceleration relative to the ground, what it asked for was the net force. And so Newton's second law says F net is equal to the mass times the acceleration of the center of mass. You don't have to draw a free body diagram if it's just asking you for the net force, because there's nothing to keep track of. The only reason you need a free body diagram is if you're breaking up the net force into individual forces. So, okay, the net force then is the mass of the passenger, 50 kilograms, times the acceleration that we just figured out, which is 0, positive 6.48, negative 2.5. And so you get 0, 324, and negative 125. And that's Newton's. Okay. So now that brings me to the important question. Why did I use Newton's second law on the acceleration relative to the ground? Why not just skip that second step and do Newton's second law using the acceleration of the passenger relative to the center? That's an acceleration. The answer is Newton's second law only holds in inertial coordinate systems. Okay, Yes. So an inertial coordinate system is one where the origin is not accelerating, and second, the axes don't change orientation over time. So another way of thinking of this is that the coordinate system is not rotating. And I've mentioned before that later we're going to talk about how to calculate true inertial accelerations if your measurements are taken in a rotating coordinate system. Okay, so if the origin is accelerating, or if the coordinate system is rotating in time, then you can't use accelerations measured in that coordinate system in Newton's second law. So let me show you an example of how this works. Okay, so here's an elevator, and here's a guy in the elevator. Elevator guy. And let's see. Actually, let me move the guy out here just for, okay, so this is still an elevator. The guy is not in the elevator. The guy is falling down. It's a really wide elevator shaft, and he's falling down it. Okay. And the elevator and the guy are both in free fall. This is really a terrible day. Plans went really wrong. But the elevator has a camera mounted on the outside. Okay. And we're going to think of that as our coordinate system. Okay. What's the acceleration of the falling man measured by that camera? Exactly. And it's easiest to imagine if they are dropped at the same time, they're going at the same speed the whole time, then the camera just sees the guy like, ah, and it's like, why is he freaking out, right? There's no acceleration, no velocity. He just sees this guy just hovering there in space. But it's even true if this guy is going 50 miles per hour and this is going 2 miles per hour. Since they have the same acceleration, that camera would see the guy falling at 48 miles per hour, but the acceleration would be 0. Okay. So the acceleration measured by the camera would be 0. Okay, so now let's do a free body diagram of the guy. What forces are acting on him? There's only one. Yeah, just the weight. So there's mg acting down. Okay. And so now if we go to Newton's second law, we have 0 negative mg is equal to the mass of the guy times the acceleration. And you can see that it doesn't hold. Okay, so to a coordinate system with the where the origin is accelerating at free fall acceleration, it looks like this guy has 0 acceleration despite the fact that there's an external force acting on him. Okay, so Newton's second law does not work in that case. If you were doing an experiment in a falling elevator, you would not think that Newton's second law was a thing. Okay. Yeah.
In space, do they still do forces relative to like Earth, or do they do it like relative to?
So there's no way to know relative to the universe. I don't know what they do it relative to, but you definitely have to do it relative to something. Yeah. That's a good question. I don't know what their ground thing is. By the way, okay, well let me write this. So if the acceleration is measured in an accelerating and this just shows an accelerating origin, but this is also true if the coordinate system is rotating. Coordinate system, Newton's second law doesn't hold. Okay, so that's why, therefore, if you're going to use Newton's second law, you have to express your accelerations in a coordinate system with first no acceleration, and second no rotation. Well, if the easiest coordinate system to use is accelerating, then you always deal with this using relative motion equations. So compared to the rotation, a coordinate system that's rotating, this is a relatively simple thing to fix. If it's rotating, we'll talk about how to do this later, but that's more complicated.
So use relative motion equations if you're not accelerating in that relative.
So basically, so the easiest acceleration to calculate in this problem is the acceleration of the passenger relative to the center. Well, the easiest one would be the acceleration of the passenger relative to the passenger. Like if he's just filming himself, then that's always 0. So that's the easiest thing. But that's accelerating, so you can't do that. The next easiest one is calculate the acceleration of the passenger relative to the center. That's not too hard. That's just circular motion. But the center is also accelerating. So now you use relative motion to do this. And if you had, you wanted to calculate the acceleration of a gerbil on a wheel, in a boat, on a thing, and all these different steps are accelerating compared to the thing. You know what I mean? the gerbil's being held by a runner, and the runner's on a stairmaster, and the stairmaster is on a pendulum, you know, all these things. You can do all these different steps of relative motion to eventually get it relative to the ground. Any questions about that? Okay. Well, what about using the ground as a coordinate system? Because, you know, the Earth is rotating, and it's also the center of the Earth is going around the sun. So that makes it seem like the Earth is not an inertial coordinate system. And actually, it's true that the Earth is not an inertial coordinate system, but it's pretty close to one. And the reason is that all of these circular motions depend on omega or omega squared, you know? So like the centripetal acceleration, the magnitude is omega squared times r once you go through all the cross products. And think about the omega of the Earth turning around, or think about the omega of the center of the Earth as it travels around the sun. The Earth going around, like rotating, in radians per second, right? That's what you measure omega in. Think of what that number is. It rotates 2 pi radians, so 6.3 radians every 24 hours. So 24 times 3,600. You know, 6 divided by the quantity 24 times 3,600 is a tiny, tiny angular velocity. And so even though the Earth is not an inertial coordinate system, you have to be measuring something pretty with a ton of precision in order to detect that it isn't. Okay, so I guess in that way we're sort of lucky. But this is what I wanted to get at, that if you're going to use Newton's second law, which is the main reason that we care about accelerations at all, because Newton's second law is the skyway that takes you from kinematics to kinetics, you have to represent your accelerations in the ground coordinate system, a coordinate system that's inertial. Who's with me on that? Yeah, so it means that if the first coordinate system you think of is not inertial, if it's accelerating, then you have to use relative motion equations. And if it's also rotating, or you know, and or it's rotating, there's another approach you have to use for that. But we haven't done that yet. So far, all of our coordinate systems have the same orientation. They're just moving relative to each other. But eventually, we'll be able to deal with things that are moving and rotating if we want. Any other homework questions? Okay, this is a big deal, and I wanted to say that today anyways. So last time, let me just finish. We don't have a ton of time left, but I can finish talking about the forces with known directions. And I gave 3 of them. Those were pushing forces, pulling forces that you can think of as always involving cables, and the third one is friction forces. We've done these 2, so I just need to talk about friction. Okay, so a friction force. the direction of the friction force is, first, it's always parallel to the surface. And I'm going to break it up into two different types of friction. So if it's kinetic friction, that means that the two surfaces are sliding relative to each other. You can think of the surfaces have velocity relative to each other. In that case, the direction of the friction force is opposite the velocity vector. So if the object is sliding this way, the kinetic friction force is this way. Okay. And the second possibility is that you have static friction. Static friction is friction where the surfaces are at rest relative to each other. And static friction is opposite the direction of acceleration that would occur without friction. Okay, so static friction, like on this chair, right now I'm putting a horizontal force on this chair. Okay, the only other horizontal force acting is static friction. If there was no static friction, it would start to accelerate that way because I'm pushing it. Okay. If there was no friction, it would accelerate that direction. So that means the static friction is acting opposite.
Static friction has been replaced by surface friction.
Right, that's right. It's either one or the other. Okay, so the magnitudes of the friction forces for kinetic friction it's always the coefficient of kinetic friction, mu sub k, times the normal force, the force pushing the surfaces together. The contact force, let's say between the surfaces. For static friction, the force magnitude is whatever is required to keep the acceleration 0 up to a value of the coefficient of static friction times the normal force. So if the coefficient of static friction times the normal is 100 newtons, okay, then say I apply 2 newtons that direction to this chair, okay? Well, you know that the static friction can't apply 100 newtons the other way if I apply 2 newtons, because that means I would push this way and the chair would accelerate the other direction. That doesn't make any sense. So instead what happens is I apply 2 newtons. The friction applies 2 newtons the other direction, just enough to keep it at 0 acceleration until I get up to 100 newtons, that maximum. And if I go over 100 newtons, then the friction can't hold it in equilibrium anymore and it starts to slide. Okay. Anybody have any questions about that?
Do you ever have to deal with rotating things and like you rotate a stapler? Because I feel like that would be really
Actually, it's the same. It's the same. In this class, I can't remember. I don't think that we have any problems in this class where you'll have to do that. But have you already taken statics? In statics, one of the last topics deals with that. Do you remember thrust bearing friction? No? Okay, well, yeah, I mean, it's not a super key topic or anything, but that's the idea of thrust bearing friction is you measure the friction of 2 surfaces that are rotating together like this, like a clutch or something, So measure the friction force as you push something to try to slow down this other thing. It's not that terribly hard, but you have to do an integral because everything has different moment arms and stuff. What? That was sort of a different thing, but it's in that same area. Yeah. Okay, well, here's an example. So let's say that you have a box on an incline. Let's say this one has a mass of 2 kilograms. This one has a mass of 1 kilogram. Let's give it an angle, but we're not going to do this calculation anyways today. And let's say that the coefficient of kinetic friction is 0.3. I meant static friction. And let's say that the coefficient of kinetic friction is 0.2. The coefficient of kinetic friction is always a little smaller than static friction. Let's draw a free body diagram. First, if the box is moving down the ramp, and second, if the box is moving up the ramp. Okay, so both of these are kinetic friction because there's relative sliding between those 2 objects. So for part A, there's a weight force. That's the weight. There's a cable force that we don't know yet. There's a pushing contact, N. And now it says for part A that the box is moving down the ramp. So what's the direction of the friction force? Yep. So it has to be parallel to the surface, opposite the velocity vector. So this is going to be the coefficient of kinetic friction times that normal. Okay. Now it's the same problem, but imagine that at that instant it's sliding up the ramp. There's a weight force of 19.62, a cable tension, a normal force. But this time, since the velocity is up the ramp, the friction force has to be down the ramp with a magnitude of 0.2 N. So friction is always trying to slow things down. You know, it never helps the velocity speed up. Any questions about that? Yes. Yes. We don't have to. A pulley with friction, all it does is add you can either think of it as a couple or so it would just be added in as like a couple. The thing that's a little more complicated to deal with would be whether the pulley has mass. But we'll talk about how to do that later too. But for most applications, you're using pulleys pulleys and cables with forces that are a lot bigger than the weights of those things. And so for most applications, treating everything like it's weightless, even though it seems like way overly simple, gives you pretty good answers. But we'll talk about how to adjust those.
So materials can help determine, like, you can have bigger friction based on the materials?
Yeah, for sure. So that's something you can like Google, like what's the coefficient of kinetic friction between smooth steel and smooth some kind of wood, and it'll just give you a number for that. Okay. Any other questions? Okay, see you Wednesday.